Hello and welcome back to this course, covering the exam topics for the JNCIS ENT certification. In this section of the course, we're reviewing high availability, what it means, and features to be used to facilitate a highly available network. In this lesson, we'll be reviewing 4 high availability software features available in some Junos devices. These are Graceful Routing Engine Switchover, or GRES, Non-Stop Active Routing, or NSR, Non-Stop Bridging, or NSB, and In-Service Software Upgrade, or ISSU. Each of these features are designed to limit the impact of failures to the flow of production traffic, therefore enhancing your network availability. Let's jump in and start off with reviewing what GRES is. Graceful Routing Engine Switchover, or GRES, is used to synchronize the kernel information between redundant routing engines. Without this configured, if a failover from the active routing engine to the backup were to occur, then the interfaces would all bounce, and there would be a delay in bringing them back up since the packet forwarding engine would restart. When GRES is enabled, the PFE does not restart, and the interfaces all remain in their current state when a routing engine switchover occurs. Something GRES will not do, however, is maintain any control plane state information between the redundant routing engines. If a switchover occurs, the RPD process must start up again on the backup RE and requires protocol adjacencies to be reestablished. So, this saves some time in restoring full functionality from a routing engine switchover, though it isn't perfect. Let's review some of the operational information about having redundant routing engines before we go over the configuration of GRES. When we have redundant routing engines in a Junos device, RE0 and RE1, they can be configured separately, using a configuration group called RE0 and RE1. These are reserved group names and will be automatically recognized by Junos and only applied to the respective RE. This is handy for applying separate management IP addresses and host names to the redundant REs, allowing for management access to both REs independently. Next, it's important that if you have a Junos device with redundant REs, that you apply the set system commit synchronize command. This is required to have Junos automatically synchronize the configuration database between the routing engines. Without this configuration command set, you must use the commit synchronize command to force Junos to synchronize the configuration states. And finally, if you don't have GRES enabled, then the routing engines will not automatically switch over in the event of a failure. One would need to manually log in to the backup routing engine and bring it online. You can enable the automatic failover using the set chassis redundancy failover command, though you don't need to worry about this if you have GRES enabled. Great. Let's see how we can enable GRES on our Junos device. Only a single configuration statement is needed to enable GRES. Simply applying the set chassis redundancy graceful switchover command and committing the configuration is sufficient to enable GRES. Recall, however, that you still need to apply the set system commit synchronize command to ensure Junos automatically synchronizes configuration changes with the backup routing engine. Once GRES is enabled, we see that our prompt changes slightly. We now have an indicator above our prompt that indicates whether we are currently logged in to the master or backup routing engine. And that's it for configuring GRES. Now, we mentioned that even with GRES, that our device will need to start up the RPD process again on the backup RE and re-establish protocol adjacencies during a switchover, which is likely to cause production traffic impact. Let's see how we can help with that particular issue. Non-stop active routing, or NSR, allows for the RPD control plane state information to be synchronized between the redundant REs. This means the routing protocol adjacencies will be maintained, essentially meaning a routing engine failover could occur with no impact to Layer 3 routed traffic flows on the device. In this case, RPD will run on both REs simultaneously, and the state will be synchronized to the backup REs. It is required that all REs participating are running the same version of Junos for NSR to work. In our diagram, we see a high-level description of what's happening, with the PFE processing transit traffic, and when protocol updates come in, the RE0 is copying the RPD state to any backup REs. Let's move on now to see how we configure NSR. First, it's important to note that it's required to have GRES configured before configuring NSR. If the GRES configuration statement is missing, you will receive a commit error when attempting to configure NSR. Just like GRES, though, NSR is implemented with a single configuration statement. Simply applying the Set Routing Options Non-Stop Routing configuration statement is sufficient to enable NSR. As we see on the right, we have committed when we have the Commit Synchronize option also enabled, and we see the commit is automatically applied to both routing engines. Great. So we now have our kernel state information synchronized between routing engines, as well as Layer 3 control plane information. However, if we have any bridging or switching occurring on our device with Layer 2 protocols, like spanning tree running, those Layer 2 protocols will still need to restart and recalculate, potentially causing an outage for your bridged traffic. Let's see how we can help with that impact as well. Non-stop bridging works just like non-stop routing, except for Layer 2 protocols instead of Layer 3 protocols. NSB supports the Layer 2 protocols listed here, essentially each flavor of spanning tree protocol. Similar to how NSR causes the RPD to run simultaneously on redundant routing engines, NSB has the L2CPD, or Layer 2 Control Protocol daemon, to run simultaneously on redundant routing engines. Then, Layer 2 Control Protocol state is synchronized between the REs. Let's see how we can implement NSB as well. Just like NSR, NSB also requires GRES to be enabled. However, NSB does not require NSR to be enabled. NSB is also implemented with a single command, simply applying the Set Protocols Layer 2 Control Non-Stop Bridging configuration statement will enable NSB. Great. The final item I want to cover before we finish this lesson is a feature that can allow you to perform a Junos software upgrade with minimal, if any, production traffic impact. The Unified In-Service Software Upgrade feature allows the device to perform a Junos OS upgrade with minimal production traffic impact. GRES and NSR and/or NSB are required to be enabled for the process to succeed. Additionally, although it's a requirement for GRES, it's worth reiterating that all REs must be running the same version of Junos prior to performing the ISSU. Performing an ISSU is just like performing a regular software upgrade, except we add the in-service upgrade flag to the end of the command, as shown here. This will initiate the ISSU procedure where the Junos OS is upgraded and routing engine switchover occurs before upgrading the other Junos OS. With NSR and NSB enabled, this should have no interruption to the control plane, with all adjacencies and control plane state maintained through the upgrade. I appreciate you sticking with me to review GRES, NSR, NSB, and ISSU. I hope that this lesson has been informative for you, and I would like to thank you for viewing.